Welcome to another GC basic demonstration. This is part 5, using a switch to set the state of the LEDs. So we're moving up, we're moving on. So let's look at the white screen. So this is a set of videos for the 18xxQ24, and this validates the compiler and toolchain for this specific chip. So please like and subscribe the videos. Those metrics are very important. It gets it to the top of the search. So if someone types in 18F26Q24, it would come to the top. If you don't like it and subscribe it, let me know and I'll change things. But these are a set of validation videos. Okay, so we are looking at this input to set the state of the LEDs. And this is, we're building upon the previous work. So I'm assuming that you've got the software all installed, programmer, Q24. It doesn't have to be a Q24. You can use the same code on basically any chip, but I'm specifically testing the Q24. LEDs, you've got a pot, and now you've got a switch connected, okay? Now, for those who just noticed, there's a typo in there. I will correct that in the set of slides. So where we left it like this, where the LED is rotating, and I can control that rotation by setting the potentiometer, and that's a delay, I think, from 30 milliseconds to half a second, sorry. And I've got LEDs, and look, I've got, for those who are observant, there's a new white cable. I've attached a switch, and that switch goes across the back into port A.3. It's got some pull-up resistors, and we'll look at that circuit in a moment, and we're moving on. So we're moving up the value chain. Okay, where have I attached that? I just said to A.3, let me bring my pen up, A.3 here, A.3. And it's connected to A3 via a 1K resistor. There is the switch itself, which pulls down to ground. And there's a pull-up resistor from the 5 volt. So it's always pulled up. And you could have a pull down, I don't really care which it is, because the program that we're looking at is actually trying to debounce that switch. So we're trying to figure out when that switch has been pushed down hard, so we can then toggle the LEDs that are attached to port B0 to B3. And you could change those LEDs as well, leaving the potentiometer where it is on A3. So what does that look like? It looks like this. Okay, so I have added in my little diagram on port A. There we go. Port A3, a little switch. So I know where that switch is attached. Good documentation is always good. And I've added in that we've got a switch spelled correctly and some resistors. So the circuit is in this PowerPoint. So what we're going to do, we're going to initialize the microcontroller. We're going to check that switch. And if it's been pushed down, we're going to do something. And then we'll go back around. Now, how we check the switch is using a function. So we've seen functions in use like readAD and readAD10, but we're going to write a function and we're going to see how it works. And then we're going to look at an alternative way of doing it. And so what it does, the chip is initialized by the microcontroller. We set all the LEDs off. We could set them to on, doesn't really matter. If the key has been pressed and it's true, okay, or if it's a no, it just loops back. If it's a yes, toggle the LEDs. It's quite simple. So all the work is in what happened here in this function called is the key pressed. So we're going to review some options in GCStudio, look at the sample code, and review the results. And then I'll show you something else as well, as always. So let's go into GC code. This is GC code. I've got the old program shut, so I'm just going to get rid of that by pressing Control W, and it just gets rid of the old file. Control B. So what I use, and there it is, 070 debounce the switch, and that's what we're doing. So we're debouncing the input. Click on that to select it. Control B to get rid of that. And there we are, we're in the editor. Everything in green is to be ignored. Quick code review. So, seen this before, 26Q24, option explicit defines the variables, and we have some constants that define our LEDs and that LED port. We set those constants to outputs. We set up the potentiometer, yes, in the previous video, but this time I've added in a switch in and we're going to use that constant in our function. And I've set that switch in to an input. And when it's down, it's set to 1. Now that's quite important, because if you use a pull-up, if you're pulling up the resistor, you'd set that to 0. So it's a way of actually changing the function operations without actually delving into it too much. So a down position, a down state is set to 1. And if you had a different wiring configuration where you pulled down the resistors, it would be a 1. So it allows you to invert the function. So let's look at the whole of the program. And here is the whole of the program. Do loop, do forever. In actual fact, you can say do forever. It's the same as saying do, to be quite frank. And forever is something that's a tie over from a very old day of GC Basic. And it says here, if the function key pressed, so it must be returning a true or false statement. If the function key pressed is equal to true, then toggle the LEDs. So why don't we just do that and we'll see it operate. And then we can look at the code, because it makes it a little bit better. There's the whole program. These LEDs are still where they were from previous, and I'm just going to press function key F5 in the IDE, and it will then just program that up for us. The LEDs are off, exactly as we expected. Now there are 4 switches in here, 1, 2, 3, 4. You can still see the white dots. And if I press it and release, press it and release, and I've used the release function, and you can change this to your heart's content. You can play with this, but look, I'm stopping the assumption that the switch has made a contact with, because I test for a release. And you can do it, you can change this so that it's a push. I just like the release personally. It's a positive push and release. And I'm checking for that. Has the key press been done, basically? That sounds quite complicated. Well, let's look at the function. The function. So if we look through the program, there's nothing in here, but remember, we can fold our code. And here is a fully documented function. And I've given you a full explanation of what it does. So there's variables. I'll just get rid of the Zen mode for us. One moment. There we go. There are some variables. The 2 variables are called current switch state and last switch state. And so we're going to compare those, and there was bits. Well, that's interesting, because we've had bytes, we've had words, and we can define bits. Well, that's pretty cool, because a bit doesn't use very much. It just uses 1 bit. And you just declare a bit. I'll show you how to do that in a moment. There's a small delay in our program called debouncing, and then we read that switch state, and depending on the current switch state and compared to the last switch state, we can return whether it's true or false, whether it changed state to the state that we're looking for. And if the state hasn't changed, it just always returns false. So you have to say, compare the last switch state to the current switch state. Those are the names of the variables, the bit variables, and you can then set it to true or false. It's a relatively simple function. And here's the actual program documented for you. So this is how we define a function, and there's an end function at the end of it. Here it is at the bottom, end function. And so we always have function, its name, function key pressed, as a bit. So even this function is declared as a bit. It's not a byte or a word, but you could return bytes or words, depending on what your requirement is. We declare some variables as bits, dimension, a variable name as a bit. The system automatically allocates a bit for you. And we might look at some assembler. Why don't we do that? Let's look at that. Press Control Shift F7, or you can press Function key F4 and type in open assembler, ASM, ASM. And in here, it will open up an internal complex file, but we'll just do a search for current switch state. Current switch state. And there's lots of things in here about current switch state, but if I just look at how it's actually done it, let's have a look. Current switch state as a bit. I'm just looking to see how it's done it. It's allocated a system variable. Look, it's complex, but it's not hard to understand. It's bit 0 of this particular variable. Look, you refer it to as current switch state, but the system automatically handles that as sysbit var 0 bit 0. And the other one is, look, bit 1. Look, there's something it's compared to on bit 1. It automatically takes away all that complexity. You just have to declare it as a bit. Right, let's just what the code. First thing it does, it checks the switch is down. Remember, we set that to a state at the top as either 0 or 1. If it's down, then it says the current switch state is either true or false. So it now knows what the switch state is. And then it compares the current switch state to the last switch state, and if it has changed, it then says, okay, I will set that function key to the result. And let me explain how it does that. It says, if the current switch state is not equal to the last switch state, cache set the last switch state to the current state. Bit invert there, but a bit of inversion, but it's quite simple. You're using last switch state so that when you come in next time, you can look for it. And then we return that switch state, because this is the name of the function. So that name, if I double click that, we can see it in blue. It either gets returned back as false on the next on the else, or it's the same as the name of the function. So we're returning our value, either true or false, into the function. And that's how it works. Writing a function minimizes your code. Look at all that complexity has been removed, and it's just called function key pressed, and it returns true or false. And you can have it return, a function can return bits, bytes, words, longs, etc. down to your requirement. But what we're doing here, as we can see on the video, in Zen mode, we're going to Zen mode. If I push the switch, I've debounced it because I know that state changed. And you'll see later on, I've got programs where I don't debounce things. You'll see things just happen twice. And if you really want to know what's going on, you need to have debounce in your switches. Inputs need to be debounced, specifically switches. Some switches are worse than others. And that's what I wanted to show. It really lays out, it resolves quite a complex problem. Let's have a look what an AI engine came up with. I said to the AI engine, define a function for me, please. And it almost ran identical code, to be quite frank. However, interestingly, it did things 10 times. It added in a for next loop. Look. Here, look at that. It said I'm going to check 10 times, and I'm going to check the state of the switch. That's switch in, the constant, which is port A3. And I'm going to read the current state, and current state versus last state. It's almost the same thing. Almost the same thing. And it's quite stunning that this has generated a very similar function, but it does it 10 times. And so I'll leave this in the PowerPoint, and then you can actually test with this and have some fun to see if it works. I'm not testing it. I just put in an AI page for you. Okay. Next video, we're going to use the reset switch. There's a reset switch on here. I'm going to show you how to use it as an input and as the master clear or the reset. With that, end of part 5, using a switch basically to set the state of the LEDs. Enjoy.